I don't know where Abraham might have told me he wasn't coming today. He might have told me that. All right. Everybody okay? Yeah, all right, yeah. We're here.
We're alive. I'm here. I'm here.
I wanna show you a story to introduce what we're gonna do today. It's a story I've told you before, but I want to tell it again now that we're on the cusp of entering the valley of isomorphism. So let's see, I've got this Cayley table here. Shouldn't need my book, my notes to do these first two. C, E, E, A, D, right? Sure. Wait, there's no D. Easy, buddy. And then that's A, and then that must be B. Right there. So check out that Cayley table. Group of size 4. We only know 2 groups of size 4, as I say over and over again. Let me put up one that looks very familiar. So plus 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 2, 3, 0, 1, 3, 0, 2. So look at these tables. And then let me let you get them written down. And tell me if you see what commonalities do you see in these tables?
You could associate 0 with E, 1 with A, and they're the same table.
And then what about the 2?
B, and then 3 is C.
Yeah. Notice that if we make these substitutions, replace this one with these symbols or replace that one with these symbols, they are the same. These are the same table with a substitution of symbols. This one is interesting because this just has that general group product here, but this one has a plus, yet somehow the rhythms are the same. So what we can do here is we can establish a map phi, and let's call this G and let's call this G bar, from G to G bar, with this setup that Sophie gave us here. So I could define it like this: phi of 0, phi of E will be 0, phi of A is 1, phi of B is 2, and phi of C is 3. Now I want to do some things with this to show you there's a richer structure that is hidden after we do that. This phi that we've set up here is what's called an isomorphism. Isomorphism between G and G bar. And this, by the way, we skipped ahead to chapter 9 in our book. We're going to come back, but we went ahead to chapter 9. I think it makes more sense to talk about this first. And so this phi is 1 to 1, and it is onto. Do you see that? That there's no 2 things sent to the same place, no 2 different inputs go to the same place, and every output is hit in the output space, looking good. But more importantly, or equally importantly, but very different, where's the algebra in this? This isn't algebra, this is just function stuff. But phi preserves the group action. And what do I mean by that? Well, let's come over here. We'll just see it in a few places. If I take phi of A times B, What is A times B in the left table?
C.
C, right? So this actually is phi of C, just because A times B does equal C. We know that. Let's look over here at phi of A plus phi of B. Now notice here, the input is inside the parentheses, so this is the input operation. This is the output operation, because we're moving from a group with this arbitrary product to a group with a sum that we're actually very familiar with. So this is the output operation. So when I add two things that have phi applied to them, I better plus them because they live over here. So phi of A is, what do we set it up? Phi of A is 1, and phi of B is 2. So this equals 3. Notice that that is exactly what we defined phi of C to be. So there's this consistency here in the way the inputs combine with the way the outputs combine. So notice that these are equal to each other. So we have this consistency. And it's this consistency that makes this more interesting and makes it more powerful in the same way. Let me just stop. Very simple example, just to kind of warm up on it. All right, where be my notes? Where be my notes? So let's get more official here about all of this. Unless there's any questions on that. Is that all feeling chill? Okay, cool. Come on. Yeah, there we go. So we say phi is a group isomorphism between groups, and you have to have groups for this, G and G bar, if phi, mapping from G to G bar, is bijective, meaning 1 to 1 and onto, and phi preserves group operations, i.e., what do I mean by that? I mean that phi of A times B equals phi of A times phi of B for all inputs from the source group G. And here I'm going to put in a little dot here. So this guy here, you might want to put in notes that this product, this operation, is the one for G, and this operation is the one for G bar. This one occurs outside phi, this one occurs inside. We're just going to do a bunch of examples today and get a handle for all this. But I got a lovely picture that goes with this. So if this is G, and this is G bar, and I've got this map phi that rolls like this. Well, if I have A and B here, so that's A, that's B, and I look at the product of A times B inside here. So these are just little arrows that are like saying connecting to the product. It's some other element inside here. Let's actually get this a little bit different. Then this guy goes to phi of A. This guy goes to, let's make a little point here for him. This goes to phi of B. And then over here, I've got phi of A times B. And that comes from this guy
but it should also come from combining these two outputs. So here I've got these two A and B's that are separate. If I look at their images over here, and then I combine them over here, this guy should equal this guy right here. So put a little note maybe that this is phi of A times phi of B. I think that picture can kind of give you a little insight in a way. It's helpful. There's so few pictures we can do with this stuff. And I got one last little table here that I think will help you navigate this stuff. So if we have this G operation, and then we have the G bar operation, and then here we have the preservation. I just kind of want to show you what this looks like. So if the G operation is some arbitrary product, and then the G bar is some arbitrary product, the way we would write this preservation is just like this. I'm not putting the dot in there, it's just implied. If this guy is dot and this guy is plus, then we have phi AB equals phi of A plus phi of B. If this guy is a plus and this guy is arbitrary product or maybe actual multiplication, then this is phi of A plus B. So see how the plus is going inside here, but it comes out as a product because the output space has this product. And then it might be that they're both pluses, and that'll happen occasionally. So this is something that I think is just good to see once. I never was shown this back in the day, so it's a good thing to have. Pretty straightforward. So if we have this, we write G is isomorphic to G bar. So you have this little squiggle. Sometimes this, some sort of squiggly shit in between them. A squiggly equals is basically isomorphic. So this says G is isomorphic to G bar. That's how I read this. You could occasionally, someone might actually put a phi there if I know what phi is to say that that's how you get back and forth. But generally what happens is you just know this and you assume, oh, there is some isomorphism, but I'm not told what it is. What it means to be isomorphic is same. You can treat one as the other. And why would you want this? Because sometimes one group is easier to work with than the other. And so I can do my work here while affecting change over here, but it's a lot more intelligible over there. Sound all good so far? Just kind of intro stuff. All right, let's do a bunch of examples. Now it's pretty much the rest of the day because we've got a lot of examples to look at and non-examples as well. And like I said earlier, I don't have an assignment for you today. Okie doke, so examples. Let's say G is the reals under addition, and G bar are the positive reals, that little plus sign means positive, under multiplication. So the claim here is that G is isomorphic to G bar. Somehow those are the same. We have to figure out how they're the same. And since we're kind of new to this, I'm going to give us some help here. So what I have to do is produce a phi that goes from G to G bar that is 1 to 1 and onto and preserves the group operations. Here's R. We could do plus, I could put a plus here. And here's R plus. So it's everything above Can you think of any functions you know of that take all the real numbers and output one-to-one and onto something that's positive?
Root squared.
Is this one-to-one?
Oh, yeah.
Not one-to-one.
What about squared?
Let's try squared. Is that one-to-one?
No.
Good, that's good, we're trying.
What about the absolute value squared?
That actually, I think, looks just like this as well.
Wow.
And it hits 0, so it's not good, right? When you input 0 for both those, you get out 0. We need something that never touches this axis here.
Log.
Like, yeah, e to the x.
Like log, but log lives here, but e to the x, yes.
That's what I'm.
The flip side. So what about e to the x? Or 2 to the x, or 3 to the x, literally any power. So you could have like 2 to the x, you could have 3 to the x, hell, you could have 3 halves or pi to the x. They all kind of look like this.
Anything bigger than 1.
Anything bigger than 1, because if it's less than 1, then we go, which actually probably would work
Do the other
too.
way too, yeah.
Yeah, so I think that really what we need is just anything that looks like that where a is positive. I think that would work. But let's go with our friend from calculus. I'm sure you miss calculus. No? I get enough calculus this semester, for sure. All right, so let's try phi of x is e to the x. So we have to address all the basics. Is this phi 1-to-1? So what we're going to do is I assume that phi of x equals phi of y. What do I have to show?
That x equals y.
That x equals y. So I need to show that x equals y here. So I'll go to the definition. Hey Sophie, what was that function you mentioned?
Log.
Yeah, let's take the log of each side.
Oh no. I've done that so long.
Oh, well, guess you're gonna like this
X
because it
equals
involves writing the word log and then being done with it.
Oh, that's right.
And these are inverse functions of each other, right? So, all good.
That's right.
Does that feel better?
Yeah.
You okay? You're gonna make it.
Everything's okay.
You're gonna make it. All right, so it's 1-to-1. What about onto? How do I do that? Somebody tell me what to write. Assume what?
Assume x equals y. Or maybe we should go the other way. Oh wait, no.
What does it mean to be onto?
Well, everything's covered.
Everything's covered, so I can hit everything in the output space.
For all y in g bar, there exists an x in g such that phi x equals y.
Yep, sounds good to me. So I pick an output from the output space, which is a positive real. I show that there's some input that hits it. We can see that there will be from this graph. We can see that it's onto, but we want to address it because we're math folk. So, i.e., given y, which is positive, solve e to the x equals y. Now I want Sophie to help me with this one, because I feel like you haven't had enough log action today.
Yeah.
Tell me how to solve this.
Log of e to the x equals log of y.
Yeah, okay, I like that.
So then we have x equals log of y.
Look at you, look at you.
Yeah.
From hater to rocking it.
Yeah.
Yeah. Just inverse function, right? Just the inverse function. So we got that. And this x is any real number. So, cool. We're good to go. Those were straightforward-ish. They probably make you pause just because log always freaks people out, but log's all right. There's worse things than log. Okay, so now what about phi preserves the group ops. So what is my operation on the input space? Addition. So, i.e. check, does phi of x plus y equal phi of x times phi of y for all, where do these x and y come from?
The input space.
From the input space. Can you check that out and tell me if that's true? And then tell me a really simple way to just explain it to someone. Why, yeah, of course that's true, because that's what we have, right? We have to check like MT423 stuff. Freak out. Laws of exponents. This just follows from the law of exponents here. Phi of x plus y, and if you're not sure, write out both these sides like I did. Like I literally just wrote that out. And then I wrote these out, and I go, oh, yes, laws of exponents. Add the exponents. The multiplications on this side, the additions on this side. So, check preserves group operations. Alfie, you are good on, good? Cormac, good? Sophie? Okay, cool, all right. These two things are essentially the same. They are the same group structures. They are essentially the same group. So I can put that R plus is isomorphic to R plus under multiplication. Those are the same beast.
Is an isomorphism an equivalence relation? Because it would be reflections, right? Would it be?
So how would you use it? How would you
Well, I guess
set it?
you
What
could
relation would you
yeah.
set up? I think we could, but
Yeah.
we'd have to get a little fancier with it. Yes,
Okay.
yes. I mean, it is among groups. So if we were looking at the collection of all groups, it does form an equivalence relation there.
Okay.
Does that make sense?
Yeah.
Yeah, cool. All right, let's look at another one. I got one for you here. What about, I'm gonna ask you this, phi, which goes from Z12 to Z12, integers modulo 12. And I'm gonna give you, is this an isomorphism? From Z12 to itself. I mean, I know Z12 is isomorphic to Z12, just with the identity, but is this an isomorphism? Is phi an isomorphism? Here. And think about the fundamental properties, one-to-one and onto. That's what, I'm gonna tell you right now it's not, just so you don't get crazy ideas. What is it failing?
Isn't it failing onto?
Yeah, it is. Tell me more.
Well, you can't hit everything in Z12 with 3x,
Yeah.
so it can't be onto.
You just hit the multiples of 3.
Yeah.
Yeah,
That's not everything in 12.
Yes, exactly. And so we could make like a little easy, nice table here. I could have Z12 elements. And then here I could have, or they could just do x. And then here's 3x, it's 0, 3, 6, 9, 0, 3, 6, 9, 0, 3, 6, 9. So this thing falls pretty woefully short. Let's write this fancy. The image of phi is just the set 0, 3, 6, 9. And that is certainly only a fraction. That is a subset, a very clear subset of Z12. So it's not on 2. It's not 1-to-1. It's not 1-to-1 because look how many different things go to 0. 3 different things go to 0. And when you have a map when you have a finite set, 1-to-1 and onto become the same. You can't have a finite set and be 1-to-1 but not onto as well, but that's like a whole other discussion. Does that, yes?
So could you say then that if you can't find a subgroup of phi that is or like a proper subgroup of phi, then
When you say proper subgroup of phi, I don't know what you
where
mean.
the subgroup, where an element of the subgroup can generate the entire, like, isn't that something where like you can, there's an element that.
You're saying all sorts of good things, but they're not combining in a way I get what
Yeah,
you're
I
saying.
don't know, I'm just thinking like, cause isn't there a thing about how like, a proper, not a proper group, but a proper subgroup, you have to have one element that can, generate every.
In a cyclic subgroup, definitely,
or
yes.
not
So
necessarily.
you're right, this is a cyclic subgroup, for sure. And this actually is a cyclic subgroup as well. Actually, right, because actually 3 generates this whole little subgroup here.
Yeah,
But you need to make sure that your generators, and we'll get to this,
okay.
but you need to make sure generator gets sent to a generator.
I think the generator is the word I was looking for.
And the fact that we're sending, like 1 generates this guy, right? In fact, we could write him like that.
Yeah.
But I'm sending 1 to something that is not a generator of this. And that's part of the problem.
Okay.
I think that if I put like a 5 here, it would have sent 1 to 5 and then that would have worked. I think that would work. The problem is this 3 is a divisor of 12 and it messes things up here
Okay.
massively. Cool question, really cool question. Any other cool questions on that?
That 1-to-1
Yes, sir.
and onto thing being the same, is that like with the assumption that the sets are like of the same cardinality, like they have the same amount of elements?
And they're finite.
And they're finite?
It has to be finite, yeah.
Okay,
so-
but like, you could have 2 finite sets that are like not the same size, right? That you could have like something, or an operation that is 1-to-1, but not onto.
True, I was thinking of a set onto itself.
Okay.
Yes,
Okay.
on the same set, yes.
No worries.
Yeah, you're right, like we could produce a not onto 1-to-1 thing pretty easily. You're right.
But you were just talking about onto itself.
Yeah.
I see.
Yeah, that's a good, yeah, is that,
Yep, yeah.
yep, cool. I'm gonna work through this one, and then I'm gonna give you one as well. So let's say that G, another example, is a cyclic group generated by some element A. I don't know if that's infinite, I don't know if that's finite. But I do know that this thing looks like this. We've got a to the 0 right here. We've got a to the first, a squared, a cubed, on down the way. Let's assume it's infinite, just for now. The order of this is infinite. So it doesn't truncate and then wrap around or anything. Here, we're gonna A minus 1. And I want you to look at this and see if you can maybe think of a great set that I could map that to in a 1-to-1 and onto way. Do you see one, Camilla? Yeah, you thinking one? Yeah. What would be maybe a natural other group? How do you, let's actually add some things. If you have an AJ times an AK, how do you combine those? Suggests to me that maybe here I've got an arbitrary group product But on the output, maybe I've got some additive stuff going on, right? So like to do this operation really involves adding some things. What do you think? Think simple, nothing fancy. It's not like some dihedral group or some that part SN or anything. Let me try to be more suggestive. I think it's good to suffer over this for a few minutes. Yeah, I'll run to the restroom. Yeah, suffer. I'll be right back.
It's gotta be, right?
Well, I was just thinking you could do like n plus one, like a to the n plus one or something.
Oh. It's just like shit.
Yeah, then everything is just shifted over by one, but it's still infinite. And it's still one to one and on to.
Yeah.
I think that might work.
So would that just be like any infinite cyclic groups are isomorphic to each other? And you can just like shift things over, just like map A to any, whatever like the identity is, or the generating element, right?
Probably, because if everything is infinite to the same order,
Yeah,
so, yeah.
so you just like map whatever the generator is to, in one set, to, like you just map A to fucking anything
You could,
in like
and then everything else is relative to it,
yeah.
probably. I don't see why you couldn't do that. Watch this be just so completely off base. It's like, what the fuck, guys?
Any suggestions? What do you think?
We were talking about maybe if you did a to the n plus one, because it's still infinite, it's just shifted over by one.
So, explain what you mean. So phi of, tell me persist.
So I guess you could do phi of, you know, a to the, a squared, or a to the 2 would wind up being, a to the third. And you'll
So
never,
like, so this is what you were saying, like
Yeah.
bump up?
yeah, because you'll never, it will be one to one and it will be on to.
That's a cool idea. That actually would work. That would be an isomorphism of this group back onto itself.
Mm-hmm.
So that essentially shifts things.
Yeah.
That's cool. That would work. And
Could you say any cyclic group of infinite order?
yes, you could say any cyclic group of infinite order, because if you had another cyclic group that was generated by some B, it's gonna have all those powers in it, right?
Just phi of A equals, or phi of A to the n is B to the n.
Yeah, can we think of, yes, exactly, phi of A goes to phi of B, whatever generates this, send the generator to the generator. What's a very simple example that we knew before we came into this class? What's the primal, the prototype infinite cyclic group? What's the prototype cyclic group of order n?
I'm gonna know what you're talking about as soon as you say it, but I don't know right now.
So here's the cyclic group of order 3, like our favorite.
Oh, just the integers.
Just the integers. This is literally just the integers.
Oh, I was gonna say,
Under addition.
well, cause I was also thinking like every group, or I guess every infinite group is gonna have the same order of infinity, which means you can just map any infinite group
So we gotta be careful, they may not be cyclic though. It
Oh.
has to be a cyclic group, as Cormac said, so an infinite cyclic group, definitely.
Mm.
And our prototype infinite cyclic group is this guy, the integers under addition. And what we're gonna do is we're gonna send phi from this group G to this group, we'll call that our G bar. And what I'm gonna do is I'm gonna take phi of A to some power. Where do you think I should send it?
1 to k.
Say it again.
I was gonna say 1 to k, because 1 is the generator in C, right?
Well, just this guy. Where do I send this guy? To K, just to K.
Okay.
Yes, yes.
Which would be the same.
It's say yes, yes.
Oh, that makes sense.
So then, when I take phi of AJ times phi AK, right, here's my everything in there's a power of A.
J plus k.
It is just phi of AJ plus K, because that's how we do it, and that is J plus K. And this is phi of A to the J plus phi of A to the K. And I preserved that operation. So understanding this, which is way easier to work with, is the same thing as this. This is just like, hey, just focus on the exponents. That group is all about doing stuff with exponents. Add the exponents, subtract the exponents.
So based on what you were saying,
Yes.
the group of all real numbers wouldn't be isomorphic because
Isomorphic to what?
itself. Oh no, it would be to itself.
Everything's isomorphic to itself with the identity map. You could just, yes.
But it wouldn't be to something like the integers
Correct.
because you can't generate all real numbers using integers.
Yeah, for example, yes, so if we took R with plus, that can't be isomorphic to Z plus, because I think what you were getting at is the cardinality of this, and the cardinality of the reals is uncountable,
Right,
but the cardinality of this is countable.
right, yeah.
So, yeah, this woefully incomparable.
So can you have something isomorphic to the real numbers, like without using the real numbers, I guess, if that makes sense?
Huh.
They don't both have to be like uncountably infinite, right?
Yeah, that's a tough.
Cause it would have to be something bigger in scope than real numbers.
I know, I was thinking, could we do it with the complex numbers, maybe, but I think you lose information when you do that.
Well, I was thinking too, cause like you could get infinitely small and infinitely, so I don't know, if you even have preservation of operation on it.
Yeah. I think, yeah, I can't think, I'm thinking of some weird things. There's this thing called the hyperreals,
Yeah.
which I don't understand. But maybe, maybe that. I feel like anything, you're gonna have a loss of information. Yeah. It's a great question. Any other questions on this? Let's look at the thing that I mentioned that I thought might lead us here, but if I have a cyclic group of finite order, then I've got a different integer set that I'm gonna work with. So if G is, another example, A, but the order of A is N. So now I have a finite order. So what does this look like? G looks like this. It's E, which is A to the 0, A to the first, A squared, on up to A to the N minus 1. What should I map that to? Z mod N. Yeah, the integers 0, 1, 2, on up to N minus 1, and then that's modulo N. Think about how that works. If you add two exponents up here that wrap you around, you're just doing modulo. You just always wrap back around. So this guy here, a finite cyclic group of order n, is isomorphic to Zn. Z mod n. Much easier to live with, much easier to think about. Sounding okay? Alright. What else I got here? Okay, this question for you. Is this an isomorphism? Let's go back to something chill, just the reals under addition. Okay, so question, example question, is phi from r plus to r plus, so the integers, the reals with just addition, this should say is, where phi of x is x to the fifth, an isomorphism in those two groups. Let me give you some time. I think the suffering is good. Just a little bit. So check through your basic things. One-to-one, on-to, preserving of operation. Thought? Yeah. I'm glad you don't think those are the same. Yeah, that's good. That's very good for a math major who's about to graduate.
Yeah.
You thinking? You're still thinking? Okay, okay.
It's one of this. It's one-to-one.
It is one-to-one. Let's write up the things as we all agree with them.
But I can't find a way to say for sure what it's onto.
Let's see, so one thing you could do, since we're working with the reals, we could just get a graph out. X to the fifth looks like that. You can kind of see the one-to-oneness, right, with the horizontal line test. Or you could just go x to the fifth equals y to the fifth, and you can just take the fifth root of each side. That's cool. On to, if I have phi of x equals y, that means x to the fifth equals y. So what does x equal to get that output?
The fifth root of y.
Fifth root of y, which is defined for all y, positive or negative or zero. So one-to-one, on to. Cool. But
It's not preserving.
it is not. And if you think it is, you are living what math professors in a more innocent time called the freshman's dream. Freshman's dream is this. That's called freshman's dream. I think I actually have seen some of the people in here freshman dream it occasionally. Back in the day. Back in the day. Once in a while, we all do this, but we know that's bullshit. Unless they're both zero, or one is one and one is zero, or something like that. There's like 3 places where that would be true. But yeah, so this does not preserve the group up. Because phi of x plus y is x plus y to the fifth, but phi of x plus phi of y is x to the fifth plus y to the fifth, and we all know those aren't the same. Yeah, cool, all right, pretty chill. How about one more? I have so much, I just like, this is all I wanted to do this weekend. I barely got your stuff graded. I did that this morning because I was just like, I just wanted to play with isomorphisms all weekend, and I wasn't really feeling like doing much else. I'm sure you can relate. So let's just do one more example and call it a day. Does that sound all right? Kind of like a mental health early day?
That sounds good.
No, Camila says no. No, she did not. No, no. I won't be able to harass you anymore, Camila, after this semester.
I know, you have to take advantage right now.
Exactly, that's right. Are these isomorphic? This will be fun. You'd probably be like, you bastard, of course you're giving us this one as the last early problem. U10 and U5. Do you know what those are?
Are those the primes?
Yeah, the relatively prime. So let's talk about what is the operation in these? Multiplication modulo 10 modulo 5. This guy is everything that's relatively prime to 10. This one is everything that's relatively prime to 5 and is non-zero. And then this is mod 5, this is mod 10. I would make the Cayley tables up and see if I see similar structure. That's exactly what I did, in fact. I think with small groups like this, that's your best first attack. Get the Cayley tables. Look for obvious similarities or obvious dissimilarities. Yes, sir.
Does our phi function have to be like numeric, or can we just say x is 1?
No, you gotta give me a phi. Give me a formula. Oh, I see what you're saying. Yeah, Cormac, you could say phi of 1 is this, phi of 3 is this. Yeah, I think that's what you're saying.
Yeah.
Yeah, you could do that. Just make sure that the group opposites are preserved.
Oh.
Which is a good one. I think that might be what I did too.
Yeah.
Yeah. so glad your pizza doesn't smell strong, Penelope. I was scared. I was really scared. I ate a bunch of stuff when I saw you had that. I was like, I better eat.
No, I needed to eat too. I forgot my lunch in my car and
Oh.
it did not sound good if I left it in my car all day.
Are you like a runner?
Yeah.
Yeah, you need to fuel constantly.
Yeah, I played soccer for 12 years, so.
Oh, wow.
Yeah, I
Yeah.
still kinda run, but it's more like Pilates
Oh.
now too, so.
That's
between
hard.
the two,
All hard work, yes.
Yeah.
No, you're not asking me a question.
This one's actually not so bad.
It isn't. There's some anchor points, right? Like, what are the anchor points? Just like really quick. Just
Well, you can map them to each other. Like 1 maps to 1, 3 maps to 2, 7 maps to 3, 9 maps to 4.
what did you say it was?
1 to 1, 3 to 2, 7 to 3, and then 9 to 4.
And then we just have to check to make sure that that works. So in other words, I got to make sure that any product of these gives the appropriate product over here. And checking all of them would just suck, kind of. So we just like check a few. So I'll check this out.
Can you try 3 times 7?
Yes, I can. So let's see. So this is phi. So phi of 3 times 7 is 1, and that phi of 1 is 1, and then phi of 3 times phi of 7, and then that is, yes, 2 times 3 is 6, but that's modulo 5, so that works out. That checks out. I think it does work, yeah, but I'm glad you guys checked it out. Has anybody checked out anybody have a different isomorphism? We'll have a better way to do this problem on Wednesday. But I think this works. And literally, if you just, I think this is what Sophie was saying, if you just replace these symbols in the tables, they become each other.
Yeah.
And that's a pretty good way to see if you actually have an isomorphism. Indeed. So just really quick, what order 4 group is this also? So isomorphism, if you know that G is isomorphic to H and H is isomorphic to K, then G is isomorphic to K. You have that transitivity.
This is
It is an equivalent. Yes, isomorphic. Yes, yes, sir. Yeah,
okay.
exactly. Yes, yeah, that really gets to your equivalence brain.
Yeah.
Yes.
So then it's just Z4, is it not?
It is Z4, absolutely. How do I know it's not the Klein 4? What does the Klein 4 have in it?
Z2 and Z2.
It is Z2 cross Z2, yeah. So this is, these are both, so this is isomorphic to this is isomorphic to Z4. What's the what isomorphism are we gonna have? So let's do Kasi from U10 to Z4. How should we do that? 1, 3, 7, and 9. Where are they gonna go?
Well, isn't that literally just what we did?
Not really.
Are you sure?
Because that's not Z4. That's
U5
U4.
is Z4.
No, U5 is modulo 5.
Oh, mod
Z4 is
5.
modulo 4. And this has a 0 in it.
Then 1 would go to 0, 3 would go to 1.
So really quick, let me stop. I like you said that. You said 1 goes to 0. Why did you say that?
1 is the identity.
Yes,
in
so-
U10.
One of the important properties of an isomorphism, we'll do this on Wednesday, is it sends identities to identities. We'll prove that. But phi of identity is equal to the identity in the other group. It has to be, it has to preserve that. So Sophie, you kind of intuitively went, okay, well 1 is the identity here, it's gotta go to 0 over here. You could actually create U10 is actually a cyclic group generated by any one of those elements in there. So check it out, because this is, 3 to the 0 is 1, 3 to the 1 is 3, 3 squared would be 9, and 3 cubed is 27 mod 10, 7. So you actually get everything in there. So if you send 3 to a generator of this group over here, like say 1, I don't want to send it to 2, because 2 doesn't generate that group over there. But if I send it to 1 or 3, I'd be good to go. And then 3 squared, I would probably need to do this, because this is 3 squared, and I want that to be the equivalent of 3 squared there, and then I would probably have to do this to get things to work out, power-wise. So it's not always just a direct, like, you know, the easiest, lowest hanging fruit possible. Seem early enough? Me too. I'll hang out, answer questions if you want, talk about equivalence relations, whatever. That's it. Get out of here. Leave. What are you doing? Go eat pizza. Go rest.